So this is an example that builds on the section 1.3 even odd decomposition of a function that we just did. So what we're going to do for this example is we're going to take a function x of t, and it's going to be a cosine, but we're going to put in an arbitrary constant phase shift. So now if that phase shift were 0, or it turns out if it were 180 degrees or 360 degrees and so on, we could show that we still have an even function. That would be a good homework exercise, is to put in a value like 180 or 360 degrees there and show that that would be an even function. Uh, but if we let theta be an arbitrary value, we don't have an even function and we don't have an odd function. But for analysis purposes, it'll be easier with the tools that we have to break x of t down into an even portion and an odd portion. So let's begin work on that using the definition that we had from last time, where we said the even portion is you take the original x of t, so there's the original x of t, and you take the version of it mirrored about the time axis. So we replace t with negative t, so t becomes negative t, and then to that value we're adding theta. So notice we did not take negative of the entire argument. That's not what the definition of even or the definition of the even part is. It says you flip it just about the time axis. So here we're getting the sum of two cosines. We know cosine itself is an even function. So when I flip it about the time axis, and I have this phase shift, I still have a cosine at the same frequency. What we expect to happen is we expect a sinusoid with omega equal to 1 and some amplitude that we're going to derive. And we expect the phase shift, we expect it to be 0 relative to a cosine, because we expect that this formula will give us an even result. So let's see if we go through this formula if we get what we expect. So we're going to use a trig identity, and the trig identity that we are going to use here is this one, cosine of A plus cosine of B. And from a trigonometry class or a table in your calculus book, or look it up online, we can show that this is a product of two cosines. It's the average of the angles, and the other cosine is we subtract the angles and divide by 2. So the sum and difference angles divided by 2. So we're going to use that identity here to simplify the even portion of the signal. So let's continue on with that. So we'll call the first angle above A and the second angle above B. So expanding this out, we're going to get 2 in the trig identity is going to cancel out the 1/2 in the formula there. And then we have our angle A, and we have our angle B is the argument of the second cosine. So we're going to plug those into the formula here, and we're going to have the product of two cosines. The first says you add the angles, and then you divide by 2. So when I add the angles, I have t plus theta plus the quantity negative t plus theta. So I get the t and the negative t cancel out, and I get 2 thetas divided by 2. So those are the steps. Whoops, 2 thetas divided by 2. So just theta. And then for my next one, it says I have the first angle minus the second angle divided by 2. So I take the first angle, t plus theta, and then I subtract the quantity negative t plus theta. So breaking it into the t and the theta parts, I have t minus negative t, so I'm going to get a 2t, and I have theta minus theta, so that term will vanish. So I have a 2t in this difference, divide by 2, so it's just cosine t. So that is indeed an even signal as expected. It has the frequency omega is 1 as expected. Phase shift is 0, as I said, making it an even signal as expected. And we figured out what the amplitude was. It was this constant that depends on the phase shift. So that amplitude number there, that could be a positive or a negative number, or it could be 0. It could be anywhere from -1 to +1, depending on the phase shift. Now, let's go on and do the odd portion. And let's do the odd portion a little differently. Instead of taking the formula we derived last time, let's go back to the more basic principle that the odd portion is whatever the whole signal was, subtract the even portion. And this is actually how we derived the formula for the odd portion last time. So we have x of t is defined as cosine of t plus theta, and we have just derived x even of t. It has this amplitude term, cosine of theta, which is a constant that depends on theta, times the cosine of t. So now what we're going to do again is we are going to use a trig identity to help us out with that. And the trig identity that we use there is going to be focused on breaking down that first term, cosine t plus theta. So we're going to use this trig identity. We have a cosine a plus b is equal to cosine a cosine b minus sine a sine b. Now we're going to use that trig identity to break this into simpler pieces and hopefully get some cancellation with this on our way to determining our final answer. So I have cosine t plus theta. That's going to be my a plus b. So going into the formula, I have cosine of t cosine of theta. Continuing in the trig identity, I have minus sine A sine B. So sine T sine theta. And then I have the remainder of the formula from above where I was subtracting off the even portion. So cosine theta cosine T. And this first term and this last term are equivalent and being subtracted, so they drop out. And I'm going to rearrange a bit here. My final answer is going to be minus sine of theta. I'm just rearranging the terms to make it look more like the other one, sine of t. So I have an amplitude term, minus sine of theta, and I have a sinusoid, which in this case is an odd function. So I can see that's an odd function. Now, to help you visualize what's going on here, breaking this cosine down into its two parts, I'm going to also post a MATLAB script that you can run and you can put values in for frequency and theta and so on and see what happens. There is one more example that follows this one, showing another even odd decomposition.